another Biot-Savart problem here. And it has several pieces to it that are nice. So, Biot-Savart, it says here, derive an expression for the magnetic field strength at a distance d from the center of a straight wire of finite length L and carries current I on it. So that distance here that we want to put the point B is a distance d away, and it has to be the geometric center of this wire here. Okay, if you change the location of P, you change the magnetic field, so be careful. It's supposed to be dead center. Now, first things first, I need a coordinate system. Straight wires do well with Cartesians. Curved wires do well with polars, and so on. Cylinders well with cylindricals. You get the point. So I'm going to choose to put Cartesians here, okay? But here's the thing. Where do I put the y-axis? Do I put it there or do I put it here? Like, it's hard to tell where to put it. Where is it better, rather, to put it? Well, for starters, let me put it here in the middle. And then I need my dl and r to be defined. So I'm going to choose over here a random dl again, like this. This is going to be my little dl guy. And it's going to get connected to point P by means of the curly r vector. Now remember what we got to fill in for the Biot-Savart law. The magnetic field that this will contribute, this little element there, will be mu naught times the current divided by 4 pi dl crossed with, you can do the r vector if you want, divided instead by r cubed. Instead of the unit vector, you can do it this way. Okay, so we go with that. What's left? I gotta find dl and r. Well, dl is fairly straightforward. You're in Cartesians, and it seems like it has a small opening here in the x direction. Call it dx. The direction of it is in the x hat. The r vector is a little trickier because it has two components right now. Well, I want you to see this distance of the dl. If you were to label it right now, you know it's going to be dynamic. As you do the integral, this moves around, okay? So you know that this has to be a dynamic variable here, the bottom one. Well, who measures distance from the y-axis? It's x. So just call it x. Simple as that. And it will be dynamic for you. Okay. So if we were to write r as a vector, I want you to see that it's made out of two Cartesian components right now. It is made out of x, but which direction? Take a look again over here. This component points to the left, and this component points up. So the x component, even though it has size x, its direction is in the negative x. These are things to be noted. So x is the size, negative x is the direction. Similarly for the y component, it is always going to be d no matter where you put that r vector. You can see as I do the integral that that does not change. It's always going to be d. So you put it here as d, and since it points up that component, you slap a y hat on it, like that. Okay, that's the r vector. What I'm going to do next is I'm going to do the cross product between these two. Here I go. dl crossed with r the vector. It's going to give you dx x hat, okay, crossed with the other one. Just copy paste it here. Okay, so you're doing a couple of cross products, and they're distributive. One of them is going to say here x negative x dx. So I'm going to write it as negative x dx. And you're crossing x hat with x hat again. But these are parallel. You already know cross products of parallel vectors, bye-bye. And then you do the other one. So you have to add here dx times d. I guess you can pull them outside as d dx. Is kind of silly. But then you have the cross product between x hat, okay, from the pink, and the green over here, the y hat. That's it. Well, what you get out of this is simple. You can use again the right-hand rule. There's the x hat, there's the y hat. If you put your thumb along here, your index along here, your middle finger should be pointing toward yourself. We call that the z hat direction when we point out of the page. That's all I got here. So the result is this distance d, dx, and then z hat. That's the cross product. Simple as that. There is few things remaining here to do. For example, I need the magnitude of r. That can...
George.
Yeah?
So you see how you have negative x dx, and then your cross product goes to 0?
Mm-hmm.
Does that mean the whole thing goes to 0?
Yeah, because it's multiplied by it. Yeah.
Oh, no, I don't know if the cross products work like that as well.
Yeah, they're distributive. If you have like a x hat crossed with like b y hat plus c x hat, you can do this cross product with that, and then plus this cross product with that.
Okay. Okay, thanks.
Mm-hmm. All right, and I always, if I can, I prefer to do the right-hand rule to find them. It's much easier. Other times, if the directions are completely messed up, you can do determinants. I don't want to do determinants. This usually gets you the things that you need. Just literally do the right-hand rule. Break it up into a bunch of cross products and do the right-hand rule on each one, and it will work out. Okay, so the only missing piece is like the magnitude here of r, and that's easy to see. Do Pythagoras on these two guys. So r will be the square root of x squared plus d squared. Now, before you get too excited to put everything in an integral and go home, I want you to always make sure that you see how the y-axis splits us here? I want to make sure that this, what I wrote down, works if I'm on the other side as well. So, because you see, I wrote that the r vector is x times negative x hat. Negative x hat points this way, but your x is now going to have a negative value here. So it's going to turn that vector around, as you can see. And you're going to get the component as it should be. The d doesn't matter. You know, d y hat, it's still looking the same. So it's still dy hat. So you build the same vector here if you're on the other side. Similarly, you want to make sure that the size works. But the size doesn't care about sign because x is getting squared. So the further you are here, even though you're negative, the negative goes away because of the square. So you see that works as well if you're on the other side. Seems like I don't have to change anything after all. I can just throw everything into this and integrate it from negative L over 2 to positive L over 2, and I'm good to go. It doesn't always play like that. So sometimes that's why I'm a bigger fan of taking the axis here at least I know that whatever I derive is going to be on one side and I don't have to worry about the other side. But here, the other side seems to be working just as well with what you wrote down here. So it's going to be one big integral instead of two integrals with something different, right? Instead of breaking it like this and this, you can go all the way across with one integral. Okay, time to go and solve it. So here I go. I got, this is just a constant, mu naught I over 4 pi. The cross product was d dx z hat, d dx z hat, and the magnitude cubed, interestingly enough, will be this cubed, basically. So x squared plus d squared to the power of 3 halves instead. Alrighty, that would be your dB. And then at the end of the day, I can actually just integrate to find the magnetic field. Now, I could have used symmetry here, and maybe I should have, to be honest with you, to cut my work down, because, you know, you're going to get one component of the magnetic field going this way. If you do a symmetric counterpart there, it will point the other way. But you know what? You can just dry solve the integral and not do symmetry here, and it will work out the same. It's not that bad of an integral. So at the end of the day, you've got mu naught I d over 4 pi, and then the integral will walk you from negative L over 2 to L over 2, integrating dx over x squared plus d squared to the 3 halves. No, not now. If you're not the average integral enjoyer, I will suggest looking at your cheat sheet here, because I'm definitely, like, even in the ones that they provide you, they're stolen from 106 half of the exams. So, I mean, if you go to the bottom of 106, so what's this? That's an integral table to be precise. And look at that. That's exactly the integral you have yourselves. So I don't have to do anything other than literally just steal from the integral table here.
Is he gonna give us that?
I hope so. He did it in the previous year. I'm sure he did it for the other group that we had last year.
Last year was a different professor.
Mm-hmm.
But if you're talking about Mike, yeah.
If he doesn't give it to you, this is a trig sub. Okay, you have to put in here would be I believe a tangent. X is equal to tangent, and it would work out. Like, you have to factor it and do a trig sub. But who wants to do that when you can just write the answer? So yeah, most of this persists, and then we recognize again what ours looks like. Instead of A, you have D. Okay, so wherever you see A replaced with D, and the sign over here is a plus, so we steal the plus. Overall, then you're going to get X over D squared, square root of X squared plus D squared, all evaluated between negative L over 2 and L over 2. That's it. Gone are these guys. I guess you're left with mu naught I over 4 pi d. Boom, boom. And then you're evaluating here. Take a close look at what happens on the bounds when you put them in. You got L over 2 there. And then you've got L over 2 squared on the bottom there. But then when you subtract, you're using negative L over 2 there on the top. And it's the same term that you're going to get in the root. because the negative will cancel to the square. So the denominators are exactly the same, and you're getting here L over 2 minus L over 2. I think you see where that's going. So at the end of the day, you get mu naught I L over 4 pi d times the square root term. It's going to be L squared over 4 plus d squared. And that is final answer. Yeah, I didn't really need to use symmetry here, you know? And I still get it just right. Trust me, you can use symmetry if you want later, and figure out that you get the exact same thing. It doesn't earn you any time, so I don't find it very valuable here. What do you guys think? Decent?
Do you think it's worth putting trig sub stuff on our cheat sheet?
You're making your own? Yes. Absolute. What do you mean? Of course, 100%. Because these integrals, you see, Neil, like they are literally all over ENM. The ones that you have here, this format, and the square roots on the bottom, they're all over ENM. Aren't you, whenever you're doing a sphere and you find potential, you're literally integrating 1 over r. And 1 over r could be made out of these things. So, and then you have integrals that involve 1 over r squared, which was ours. And that's where you get these kinds of integrals, right? So, if anything, I think that these 4 are an absolute must over here. The ones that are talking about roots. Let me show you which ones. I would say with certainty these ones. All right. Yeah. The other ones over here are easy. You can do them. Like, you don't need to have them on a cheat sheet, right? But these ones eat up a lot of time if you don't have them on a cheat sheet. So I'm just leaving them there in the recording so you can see them. I can also screenshot them in the file. It doesn't matter.
Just did.
Oh, you did? You're fast. Damn. All right. Let me grab that. For the rest of you, I'll put this in. All right. Any questions on the one we did, though?
No, not for me.
Jeffrey? Alina?
Yeah, all good with me.
Did you follow it, Alina?
Yep, I'm good too.
All right. So definitely include these on your cheat sheet. They happen all the time, and you're not going to be happy to find out that you need to do one of these on the exam. Even though it's doable, you don't want to do it. Just trust me. So he will literally give you 0 marks for doing it. You earn nothing. All
What
right.
if we don't get the final answer?
No, you earn nothing by showing him how you do the integral. He literally will not care.
Oh, okay.
Yeah, which kind of sucks, and you don't want to be that guy, you know? I'm just adding the z hat here because I had forgotten it. But other than that, that's your magnetic field at that point. Maybe I'll consider that as a separate video here, deriving this magnetic field.